So next speaker is Antonio Hales, and will tell us about ALMA studies of young eruptive stars.
Thank you very much. My name is Antonio Hales. I'm a scientist at the National Radio Astronomy Observatory, although based in Chile at the joint ALMA Observatory. And I want to thank the organizers for giving me the opportunity to come here and share with you some of the research we've been carrying out on the field of young erupting stars. We've heard excellent talks already this week about what FU Orionis stars are. So I'll briefly repeat more or less what we know about them. These are stars that suffer very dramatic increases in optical brightness that are mostly attributed to enhanced accretion. They cannot be explained by just extinction. And the interest about these stars have been growing rapidly in the recent years, mainly because they came to as a savior to reconcile the luminosity problem in which young stars appear underluminous compared to theoretical predictions. And it's now believed that most stars at some point will undergo one or several FU Orionis or eruptive events, and in which the stars can build up a significant fraction of the total mass. It was also pointed out already this week that these eruptive events may have dramatic effects on the disk material itself by changing the properties of dust grains, that was shown by Peter Abraham in these changes in crystallinity of the dust grains in the mid-infrared. They can also affect the location of snow lines, which can also in turn enhance the ability of dust to coagulate and form planets. We now believe that outbursts are common. There was a strong bias originally to detect stars mostly in the optical, and the discovery of FU Orionis objects was mostly led by amateur astronomers in the 60s and the 70s. But today, the role of amateur astronomers has been supplanted by systematic surveys, and we are discovering eruptive stars at a rate of about 1 star per year. And they're probably going to increase as we continue surveying the sky. As I said, there was an optical bias towards visible stars, but now with systematic infrared and submillimeter surveys, we are discovering that eruptive phenomena go down to even the class 0 phases, as has been shown by the works with Spitzer and recently by the work by Doug Johnston using the JCMT, in which they discovered that about 10% of class 0 protostars show increases of about to 5% in the submillimeter luminosities. Eruptive stars have been classified into 2 kinds and 2 subgroups, XORs and FUORs. XORs have been misnamed after their prototype, XLUPI, and they show smaller and shorter increases in luminosity compared to the FUORs. They show increases in 2 to 4 magnitudes in the optical magnitude, and their duration lasts from a few days to a few months. In quiescence, they look pretty much like classical T-Tauri stars. Most of them actually have class 2 SEDs. But in outburst, the emission lines brighten and the photosphere is veiled by an accretion flow, and that fits in very well in the classical picture that we've seen many times this week of magnetospheric accretion, and by being explained by enhancement in the accretion flows during the outburst. So here's the light curve of XLUPI itself, which show that it went up a couple of magnitudes and then went down within a year. FUORs, they suffer longer and bigger increases in brightness that correspond to sometimes even a factor of a south in increase in the accretion rate. And photometrically, they are a more heterogeneous group. Here's the FUOR itself. It went up in the 30s and has been very, very, very slowly fading away and during the last 80 years. Whereas if the more stars we discover, the more heterogeneous the group gets. As, for instance, HBC 722 that went up, but then went down, so people thought that originally this could be an XOR, but then it went up again and stayed again in this enhanced accretion level. So it's actually much easier to catalog the stars based on the spectroscopic features that were discovered in the 70s. And some of these spectroscopic features are that the stars seem to have a gradually cooler spectra as you move towards longer wavelengths. And in addition, most of your stars, they show these double-peaked absorption profiles that can be better explained, as was pointed out before, as the presence of a superluminous accretion disk, which is the models by Lee Harman and in this case of Xu et al. That can explain the SEDs and also the spectroscopic features of a few Uranus objects. In addition, as was pointed out by Agnes Kospel earlier on, most FURI stars are surrounded by reflection nebula that seem to brighten up during the outburst. And that's how, for instance, this star was first discovered by the amateur astronomer Jim Toms. He saw that there was this reflection nebula and this brightening up of the star. And they are also surrounded by P-signal profiles that indicate that strong winds are emanating from these stars. Because of all these properties, FUR objects are usually associated to class 1 protostars. Many of them have class 1 SEDs, although there are a few FUR objects, like FUR itself, that has more like a class 2 SED. Because of the intensity of the outbursts, these are usually associated to some sort of large-scale disk instability. And we heard an excellent talk yesterday by Edward Boroyev showing the different mechanisms that could explain these outbursts. I'm not going to go into detail. I think he really covered all the bases. But what is clear is that most of the predictions show very distinct signatures in the disks, in the accretion disks themselves. So to be able to distinguish between the different predictions, we need to study the disk properties. Before ALMA, there were only very few disks that had been resolved. I actually had to go back to these Karma millimetric observations in 2010, in which they used a rather nifty phase calibration technique to be able to resolve the disk around the PP13S. One of the outcome of these observations was there were no obvious clumps, and the mass that they derive, assuming optically thin emission, which we know now it's not a good assumption, is that the disk is very low mass compared to the predictions of gravitational instability, for instance. Another result from these surveys is that the XORs were mostly undetected, so pointing out to even lower masses in this type of eruptive sources. Millimetric observations also identified as early as in the 90s that most FURs were surrounded by prominent outflows. Neil Evans used the CSO to map a series of FURNs objects and found outflows in all of them except FURNs itself. And Agnes Kospel and the collaborators in the Concolli Observatory, who have been really driving the field in the last 10 years, have used also APEX and the Plateau de Bure, now called NOEMA, to confirm that most FURNs objects are indeed surrounded by prominent outflows. It is with this motivation that we use ALMA in cycle 2 to survey a small sample of 8 eruptive sources, 3 FURNs and 5 XORs. And we detected all of them with ALMA, thanks to the exquisite sensitivity of the instrument, but we found no structures in the disk, at least at this resolution. This one here, it's actually a binary star, so it's not really a clump, as we would have liked to see if this was being due to gravitational instability. We did not detect gravitational instability signatures, not in the brightest disk. The brightest disk is this one here, V883 Orionis, which, as Simon Casassos showed yesterday, we followed up at very high resolution. We managed to convince the TAC that it was a very good candidate to detect gravitational instability, but we didn't, right? What we detected instead was this relatively smooth disk with this sharp transition that, as Simon pointed out yesterday, can be interpreted as the location of the water snow line. We also followed up recently HBC 494 at much higher resolution and detected that it's a binary. So binarity can still be one of the candidates for explaining the eruptive phenomena, at least in the ones we know are binaries. Of the disk we can resolve, we were able to place limits on the radius and the radii of these disks using radiative transfer models, assumingly the standard model of a passively radiated accretion disk. And with that, we can place them in this sort of mass versus radii plot that was first shown by Lucas Cieza, in which we can see that the FURs are definitely brighter in average than the XORs, and also brighter than the typical class 2 disks shown in Taurus. Here in green you have the eruptive sources, and in red are the class 2 disks from Taurus from Sean Andrews' survey. We recently updated this plot with a few more stars that we've been studying, the two prototypes, FURI and XLUPI, which both of them sort of look like class 2s, at least based on their SEDs, but the trend is more or less confirmed. Another very interesting result from the simulations that were performed by Sebastián Pérez, who's going to be talking after me, is that according to the radiative transfer model, all these disks are not only compact, but very optically thick in their inner cores. So any estimations of the mass must be taken with 1 or 2 pinches of salt. The trend that we find with ALMA was confirmed by a larger survey carried out by Bob Lute and collaborators using the SMA, in which they find that the outbursting source population is indeed more massive and brighter than the population of class 2 disks. And compared to, if we put them in the context of more protostars, they lie right in between what we expect from class 2 disks and class 0 and class 1 protostars. So giving us an idea of the evolutionary status of these disks. As a byproduct of our first survey, like most people do, we said, well, let's put in some molecular lines as well. They come for free in ALMA if you put them in your correlator configuration. And we were not expecting to be studying outflows, but as a serendipitous discovery, we discovered that all three FURI stars that we observe are surrounded by prominent outflows, which are actually slow-moving and very wide angle if you compare them to normal class 0, class 1 protostars. We observed recently 4 more stars, 1 XOR and 3 FURs, just to try to understand more about the diversity of the circumstellar environments of these stars and how they may be affecting the outbursts. So we see outflows here, right? Very wide angle again. This one has a conical shape that has also been observed by Takami-san and his collaborators. He just published a paper on that. You can see the outflows better here, but they had much better integration, so they can study much better what's the environment of that star. Whereas we can see that we have outflows here. This is kind of messy, but the top one is clearly a Keplerianly rotating disk with no signs of outflow. So sort of reinforcing this idea of FURs being younger than XORs. Here I'm putting this slide just to talk a little bit more about these two sources. GM Cha really looks like a class 1 star. This is the discovery of the outburst paper. I thought I should show 1 or 2 light curves just to win the audience. Whereas US Tau, it's a well-established and well-studied disk, has been recently observed by the D-Sharp campaign. And looking at the light curve, it's really hard to trace back when it was decided that this was an XOR star. This is indeed a quadruple system. Here are 2 binary stars, and this is a spectroscopic binary. So again, the idea that binarity may be playing an important role on the triggering of the variations on the light curves and on the accretion of these stars. We also observed the prototypes. This is FU Orionis. the first star that was discovered. And as I said earlier, Hales, in his 1994 paper, said that there were no outflows around the star. We observed it in cycle 0. This is the SCD of F Orionis. And it does have, at least from the SCD fittings and from Herschel observations, a small envelope component. Right? So we were a little puzzled when we didn't detect anything larger scale in the cycle 0 observations. This is the integrated intensity map of carbon monoxide. So, as you know, the interferometers, they tend to filter out large-scale emission. So we decided to follow up this observation, this target with the ACA, ALMA compact array, and total power observations to show that actually the star does have prominent wide-angle outflows like we see in other F Orionis stars. In grayscale is the scattered light reflecting nebula of F Orionis, which was actually how it was discovered also that was also discovered after the outburst of 1936. Sebastian is going to be talking after me in detail about the high resolution observations that we have about system. Actually, right here, that dot is 2 dots. That's the continuum emission from the high resolution observations from Cieza, in which we resolve the 2 disks. And you'll see that the kinematics is going to show it's sort of consistent with the outflows going into those directions. To really understand the connection between outflow and optical variability and the triggering mechanisms, we need to understand and do better models of how outflows work. I am coming from the disk community, so it's the first time I have to deal with outflows, but I'm working with Hector Arce and Jonathan Williams to try to apply the models that have been applied to other class 1 objects to understand and understand better what's triggering and what's causing this outflow. What we can do for now is that we do have 13CO and C18O, so we can use the standard method for correcting for opacity effects and estimate the properties of the outflows, as we've done in the other sources, to infer the total outflow mass and the mass flow rates that seem to be consistent with what have been measured by other authors using optical lines, and that show that they are indeed higher than what we've seen in classical Titori stars, at least. So we also observed Xlupi, which is the other class prototype. This is the light curve. This is the SCD that I was telling you. This is very much of a class 2 disk. And Ines Kospal had already studied the star and detected the molecular lines, which can be well modeled by Keplerian disk, which is what you see in red here. So it was not surprising that the CO emission did look like Keplerian rotation. This is a model of a Keplerian disk. At least the red side of the disk does look like a Keplerian disk. However, we did discover that there was a strong asymmetry on the blue side of the disk, and even this sort of a arc-shaped outflowing material that can be explained as some asymmetric outflow. So this is the first time as we find evidence of this sort of outflow activity in an XOR, and we really need to observe more targets to see whether there is a connection with the XOR phenomena and the outflow and the asymmetry on the disk. There seems to be a very strong clamp there that it's not clear how to interpret without the proper hydrodynamical modeling. So to wrap up, I thought I'll put together this ALMA gallery of eruptive sources. I think I tried to put them as the more collimated to wider angle to the XOR that shows the diversity we have and why we need to be observing more sources to try to understand the eruptive phenomena from larger to smaller scale. Because, as has been demonstrated by previous authors, by Arce and Sargent, and also by Takami-san, if you put together many eruptive sources, at least the collimation angle, the opening angle of these outflows seems to be widening with age. Although Edward already said that age is somehow flaky, but they didn't seem to be fitting with this idea that as the star evolves, it pierces through the envelope and starts opening the cavity until you see something like what we see in Ex Lupi. Interestingly, Takami-san has been pointing out in 2 papers that what seems to be here a one-way street may be a two-way street, in which when you reach this state, if there is more material in the cloud, they may go back to this stage in a kind of cyclical phenomena until all the material from the cloud has been removed. So, in summary, we have discovered that most disks around the F-Urin stars are very compact. We don't see very evident clumps or any substructures as they are predicted in the models. Although Edward did mention yesterday that these instabilities may be happening even in the embedded phase. So what we really need is means to pierce through the optical thickness of the clouds of the disk to see what's happening probably in the terrestrial planet zone. And this is what we need, observations at lower frequencies with even higher spatial resolution. And that's why we are trying to arc for the next generation VLA. But I thought rather than having conclusions, I'll finish with open questions that may be more relevant to the scope of this conference. I mean, we tend to put things into boxes. We love putting things into boxes and labels, but are they really that hard, the distinctions? For instance, how many eruptive sources do show UX or phenomena? There have to be some variations due to extinction itself, and that was already shown in the case of V582 Auriga. And if we also look at F-Orionis itself, it also seems to have like smaller amplitude variations that can possibly be attributed to extinction effects. And that's why we need more studies like the one that was done by Peter Hebrim and collaborators, in which with the proper photometry and the proper measurements, one can distinguish between what is accretion and what is extinction. Thank you.
Thank you. Questions?
The ALMA simulation, the ALMA observations track the ground dust, right? And a priori objects usually have rather large masses. For instance, greater than 0.1. So theory predicts some structures, right? What is the reason of this discrepancy? Maybe the ground dust doesn't really track the global mass distribution. What do you think about it? Yeah, in the disk, yeah. Yeah, the masses of fours are usually more massive. The masses of 4 disks are usually more massive than higher than 0.1 solar mass. For such a massive disk, we expect, not only for my models, for many other models, we do expect development of gravitational instability, some spiral arms or something. But the ALMA looks at the ground dust. This is not the main reservoir of mass. This is like 1/100th of it. So the total mass is in gas. Is it possible that what we see is not the true distribution of mass in these systems? So the gas may have still some substructure, but the dust doesn't have the substructure. This is one question. And second, did you see any ring structures, gaps in the case of dusty disks and FURs?
Thank you. This is actually total disk mass, assuming 100-to-1 gas-to-dust ratio. Okay, so we used the dodgy part here. Well, there's many assumptions. Okay, we assume it's optically thin, which we know it's not true. But but this is total disk mass. So the 0.3 solar masses that we see here is the mass that we derive for the total of the system. We also have, on this particular disk, we do have 13CO and C18O observations that resolve the disk. So we use that to estimate with a grid of radiative transfer models, the ones from Williams and Best, to estimate alternatively the mass. And it's a very massive disk. That's how we got the follow-up observations. We said we're going to resolve the gravitational instability, and instead we found that the disk is very smooth, which is the Nature paper by Lucas. It's not the best contrast image, but here there is no really a ring, but there is a strong change on the surface brightness profile. So that's one interpretation. The one we gave in that paper is that it may be a change in the snow line, but maybe if you observe it at another frequency, you may see it as a ring. Of the other follow-ups, we have not seen anything else. They all seem to be very compact and in size.
Sorry, if you see, just in case FU Orionis, some kind of infall, so it's assumed that this is early stage, and then we see so-called loaded disks, so infall of matter onto the external regions of the disk. If we have any evidence for this, in the case just FU Orionis.
Thanks, Sergey. That's an excellent question. And Sebastian is going to be showing what we've found out from very high resolution observations of the disk, of the gas kinematics around the binary star.
So I will see.
Yeah, it's complicated. That's what I can anticipate.
Okay, any further questions? Vladimir?
Can you show again the slide with H-alpha line in the spectrum of V1057? Yes, this, yes. For irradiate optical radiation from the disk, accretion disk. Accretion disk is optically thick due to the strong mass accretion rate. And in this case, the part of the outflow which move away observer will be screened by the disk. In such a case, we will accept only the blue shifted absorption and any emission, red emission. And spectrum of FU Ori itself demonstrates such a profile. Absorption and zero emission, red shifted emission. But in this case, we have almost classical Pezigny profile. We see the emission, the red shifted emission, which cannot be observed if the disk is optical thick. This is not very clear for me how to explain this. But situation is very simple. Yes, optical thick disk it screen all that move away from observer, and we see only the part of the outflow directed to observer, blue shielded absorption. The emission cannot be observed in this system, but we see it.
I think there must be some inclination effects also going on.
Maybe this is a binary system. Maybe there is another source of emission. Not.
Okay, we can continue this in the break. And last question.
FU Orionis is binary.
Very wide.
How wide?
200 astronomical units.
150.
Okay, there's another question.
But there is an indication that might be a spectroscopic, yet another spectroscopic binary within the prime. I've seen some waves. Yes, still unseen.
Okay, a short comment to Vladimir Grinin's question. The emission you see on this picture is highly variable. It's my picture from my paper with George Herwig. And in some days of observations, the emission was completely absent. So it's a highly variable emission. But it's rather weak as compared to a normal T-Tauri star. So it's not clear where it comes from, really.
Okay. Any further questions? Yeah, if not, we can also discuss them in the break, and we will continue then 4:10. Okay.